The output from our generator, the generator goes to the circuit breaker, which is located in our switchboard. So paneled off, we can just see the front of the circuit breaker. It's a dead fronted panel. So the three phases are connected through to our main circuit breaker, and then when the circuit breaker is made in, it puts power onto the buzz. So from the main circuit breaker, power is fed to the main buzz, and from there, this power is fed by the distribution system that you've got on board to the circuits that make up the vessel's electrical system. We take this via distribution boards, various distribution boards, and rather than having loads of big cables running all over the shop, we can just take one big cable through to a motor control center or motor control, which will just be central, and then we can take off the drives for each individual motor. The nominal 4-volt three-phase supply can, and very often generally is transformed down through a step-down transformer to give us a typical 220-volt circuits. Generally, they're single phase, which power the lighting systems, for example. Okay. The problem with electricity is it's dangerous. So as long as everything's insulated and kept behind where it should be, we don't have a problem. But one of the big problems, an ongoing problem, which is a bit of a headache for ships engineers, is earthing. Yeah, earthing systems are required. Ships, yachts being no examples, predominantly have an earthing system which is called an insulated earth system, i.e. it doesn't go straight down, the short doesn't go straight down to the earth, which would be the ship's hull. Okay. Why do we insulate our pieces of equipment from the ship's hull? Well, if we didn't, as soon as we got an earth or a short, we would lose electrical power. That's not what we want on board a ship. If we were on land, yes, then it's there to protect personnel, people working in a factory or wherever it is. But on board, we don't want to lose our critical equipment. Example, the steering gear. Bump, it'd be gone. We'd black the ship out, knock all the power off, and we would lose control of the ship. So we don't want that to happen. So we have what we call an insulated earthing system. Should an earth occur in one line, red, yellow, or blue, one of those three phases, then you would get an alarm on your earth monitor, but nothing else would happen. Doesn't mean you've then got to go out and find where the earth is, which is a problem, but it needs to be done. But it won't black the ship out. In order for that to happen, you would need a second earth on another line. So if you had a first earth fault on the red line, if we got a second earth fault on, say, the blue, then you would actually interconnect the two earths through machinery, and you would actually lose your power. So, safety, let's look at protection. Yeah. Why do we have circuit protection in our electrical systems? Well, one thing we need is protection. If something's going faulty, we want to disconnect it, get it out of the system. Okay. We want to ensure that we maintain power supplies to our healthy circuits without shutting everything down. We want to prevent damage to the equipment. Okay. And lastly, and probably most importantly, we want to protect ship's personnel. We don't want people to get electrocuted. Systems are protected by various means, by circuit breakers and or fuses. And these are all rated or set. They will break or at a predetermined level of overcurrent. The protective device will, as I say, activate when the line current, the IL line current, exceeds the full load current, which we would expect to find under normal operating conditions, by some factor, whatever it is. Okay, and circuit breakers operate on the switchboard in a number of ways. Generator protection itself comes in a number of forms. We have an overcurrent inverse time, which that means that the bigger the current, if we measure time up there and the current along there, what we get is a curve like that. Yeah, so if the current is very, very high, it will cut out in a short time. And if the current is lower, then we will put a time delay in and it will shut down in a longer time. Okay, that's the first one. Overcurrent inverse time. That forms part of what we call the protective discrimination system that's on board. Okay, now these times vary. It depends on the size of the voltages and the currents involved, but typically you're talking about a delay of maybe 1 to 20 seconds. Secondly, an instantaneous current protects against short circuit, okay, where we get a very, very high current. You can get thousands of amps going through the system, yeah, and that will operate somewhere between 2 and 10 times the full load current, and it will bang, yeah, it will bang it out, shut it off, probably in less than 1 second. Other protection devices we have on the generator, which are shown on the switchboard, are under voltage and over voltage, and those typical values are 80% of the line voltage up to about 120% of the. So in that area there, if we go below or above those figures, then your under and over voltage trips will cut in. We also have under frequency, excuse me, and over frequency systems, and they're normally set approximately 4% above the stated frequency at which we're operating the system at, 50 or 60 hertz, whatever it is. The one that most of these you can't really test. Yeah, you have to, you need specialists, certainly over current trips. But one you can check on a regular basis is the reverse power relay. Okay, a reverse power trip basically monitors the direction of power flow through the system through two transformers. There's a current transformer and a voltage transformer, and when everything's working nicely, this sets the pattern through. The transformer holds in place basically a rotating disc, yeah, and it maintains the circuit through it. So it holds the relay in position, basically. If the prime mover fails, then the generator would actually try what the power from the buzz would try to power the generator. So instead of the power coming out of the generator into the buzz power would try and make the generator operate as a motor, which is not desirable. You will black the ship out if that was to happen. Okay, so the reverse power trips operates the circuit breaker. So that sums up. There are other protective devices, but they're the main ones that you need to think about.